the context of fluid mechanics. So validation is the assessment of the accuracy of the computational simulation by comparison with experimental data. It has been considered very important for numerical models being validated against experimental data. However, it has always been a challenge to do. So sometimes people just don't have the data available, and a lot of times people have the data, but it's not exactly a good match for the numerical model that they're doing. It is also said that, quote, validation has the highest priority because nature is the final jury, unquote. However, like I said, that being understood among a lot of numerical modelers, it is very hard to find a good validation data set. And it is important to not confuse validation with verification, because the first one, verification, is a process to verify if the equations were solved correctly, so to verify the math is correct. However, validation is a process to make sure that we are solving the right set of equations, or we're solving the equations with the right numbers. So even if a set of equations or models are verified against analytical solution, it doesn't necessarily mean that it will be representing the reality when it is applied to a real life problem. So that is where validation comes in. So let's reiterate a little bit of the basic concepts of computational fluid dynamics, also called CFD modeling. So CFD modeling is a numerical method that uses numerical analysis and data structures to analyze and solve problems that involves fluid flow. And CFD modeling specifically solves the Navier-Stokes equations, which usually include a continuity equation and a momentum equation here. Now we have basically two big ways to solve the Navier-Stokes equation. The first one being direct numerical simulation. So just simulate the equations directly, no models, no approximations, just solve it directly. And as you can see, it's pretty difficult because the Navier-Stokes equations are nonlinear and partial differential equations, and it requires a large computer power. So with the computer power that we have nowadays, doing direct numerical simulation, or DNS, it is only possible to resolve the flow to a Reynolds number up to 10 to the 5, I think, and that is in nature a very not turbulent flow. So most of the flow in nature are 10 to has a Reynolds number of 10 to the 5 or higher. So another alternative is to solve it using models and approximations. And here comes a lot of turbulence models. And I'm sure people are very familiar with the Reynolds average Navier-Stokes equation, which is called RANS. And also the large eddy simulation called LES. With RANS, the way that RANS solves Navier-Stokes equation is that the model, the terms that are unclosed in the equations, which is the Reynolds stress terms. And if it's in 3D, you have 6 Reynolds stress components. And that's where the models come in. And LES, large eddy simulations, are basically DNS, but to a certain turbulent scale. So with a scale that is less than determined significance, LES model would just model these fine turbulent scales, so using some subscale modeling. And also we have a coupling between RES and LES. I would leave it there. Another way to approach fluid mechanics problems is to just study it using experiments. There are various strengths and limitations with experimental study. The strength being first that is a real fluid flow, so it's real water, real air, within a real physical structure, so like a wave flume or a water channel, or if you were to conduct experiments like, like here within this channel, we were studying the flow structure or the flow behavior around some high sidewall baffles. So we're installing actual real baffles. So all of these, the strength of the experiments, namely they would represent the true physics of the flow. So there is no way that you would have water just flowing to the air out of nowhere, or you would have a jet of water just coming into the channel out of nowhere unless you put it there. But this could happen in numerical model if you are not careful with your boundary conditions. So the strength of physical modeling is that it is real, it is physical. There will be nothing that is against the rule of the real world that is happening in a laboratory. But some limitation too, as you can see in those photos. First, you may have intrusive instrument, and a lot of instruments in physical modeling can be intrusive. And when it actually goes into the flow, it would unavoidably disturb the flow. And that is one limitation of a lot of laboratories. And also, the instrument can be a black box. So for example, the acoustic Doppler velocimeter, also called ADV, they are basically a black box. All the electronics, all the hardwares were sealed, as you can see here in this little black box. So unless you engineer at the same time as electronics, otherwise, when you get a set of data that is wrong, you don't really know why it's wrong, and you have to send it back to the company, and the company said, oh, okay, we don't see what's wrong with it, and then they send it back. And even your data seems correct due to the same reason, you're not 100% confident why and why or whether it is correct. So that is one limitation. Another one is aeration is almost always a problem. So nowadays, a lot of people are using laser techniques like particle image velocimetry, also called PIV. People should know it pretty well if they were working in the experimental field. Also, the laser Doppler velocimeter, LDV. But most of the laser techniques, they don't work very well with a highly aerated flow. So if your flow is half air and half water, all those techniques could be unreliable. And nowadays, to the best of my knowledge, I don't really know if there is an instrument that could be first unintrusive, and second, deal very well with two-phase or even three-phase flow. Sorry. So so how do you compare experiment with numerical model? Then how do you exactly validate what you have numerically and experimentally? Well, I had the fortunate experience during my PhD to do both numerical modeling and experiments at the same time. And another instance is during my first project for my postdoc, I was able to do the same. I had experiments and numerical modeling experiences. So I was able to use these experiences to basically sum it up into two case studies here. And I'll show you the process of validation, and it is sometimes complicated and it's sometimes just a pain. So the first case study is breaking wave or breaking bore or breaking surge. So this is what I've done during my PhD. A breaking bore is a form of wave breaking in rivers and estuaries. It can be found in over 400 rivers worldwide. It happens at a very particular natural situations where you have to have a large tidal range and a very specific funnel-shaped river mouth. so that when you have a tide rise in the ocean, it has to squeeze its way through this funnel-shaped river mouth and go into the river, and thus form these beautiful walls of water, and then propagates upriver. So as you can see, a bore can be of different shapes. It can be angular, like waves, like shown in this picture, or it can be just very breaking, as shown in this one. Either way, the very turbulent processes involving a lot of mixing, scouring, sediment transport can be responsible for the riverbed and riverbank deformations, and it can also be responsible for the change of habitat of all the river animals and fish, because they propagates upriver, so they propagates against the main flow. Experimentally, you can study this phenomenon by having a long channel and having a rapidly closing tensor gate at the end. So you can have initial flow going here as in this picture from right to left. And then by rapidly shutting the tensor gates at the left end of the channel, you generate a breaking wave or with a specific combination of flow rates and initial water depth. You would be able to generate a breaking wave that propagates upstream of the channel. So to study this, we can use acoustic displacement meters, also called ADMs here, to measure the free surface. And these are non-intrusive, by the way. And to measure the velocity, we can use acoustic Doppler velocimeter, or called ADV here. This is actually an ADV profiler, so it's not exactly a traditional ADV, but we won't go into too much detail here. So as you can see, this is an intrusive instrument. So it goes into the flow. So it would, and it actually has a pretty complicated shape. So it would disturb the flow physics a little bit. And because the flow is unsteady and rapidly varying, so it is not possible to do time averaging in this case. So we have to repeat the experiments a lot of times. And here we use 25 repeats, according to previous studies, where basically a sensitivity analysis were carried out, and we determined that 20 repeats is the minimum requirement to get most of the turbulent characteristics right. So going to numerical studies, specifically CFD, I used large eddy simulation in this case to simulate the breaking wave. I used three experimental data set as the reference, boundary, and initial conditions. And because this is a two-phase flow, so I used VOF for resolving the interface between air and water. We used a finite volume method for the discretization, and both 2D and 3D simulation were carried out. So as you can see in this, this is just a schematic for the numerical domain. So we have here is the inlet. On the right-hand side is the inlet. On the left-hand side is a wall, just to simulate the closing gate. On the bottom is a wall. On the top, we use the sleep condition. And the lateral, so with the 3D, we just imposed a lateral dimension where we used the width of the physical channel, and obviously all the lateral walls are modeled as walls. So this is an output from the 2D simulation. I was wondering if I can slow it down. Sorry. I was wondering if you can slow it down a little bit to see the generation process. So as you can see here in the generation process, you have the water piling up and then become like a wall of water with a bit of with a small head here. It hasn't been aerated yet, but then as it propagates upstream, it starts to get aerated, and then you start to have the water breaking. So if you look at the same flow condition, but experimentally, it's actually pretty close to what happens experimentally. So you would have a wall of water coming up, and then have like a small sort of, I don't know how to explain this, but you have the wall coming up first, and then the aeration happens next as it propagates further upstream. So here in the middle of the channel, as you can see with the experiments, yep. So with experiments, you can see the breaking roller that's probably going so experimentally, the roller is taking up pretty much the whole height of the increased water level, whereas in the numerical model, it seems that you have a bit less aeration happening here. And also in the numerical model, you see there is elongated sort of structure in the front of the roller, whereas experimentally you don't really see that. And again, you have a lot of aeration in the numerical model that never goes away, so they just stay in the water and keep rotating. I think that's the inherent problem of the model there. Sorry, I forgot to mention, so the numerical model, the CFD model, were carried out using the code TIDIS that is developed by the University of Bordeaux. And now they are developing a brand new software called Notice. But by the time they were still using TIDIS, this is a well-known problem there, that they don't have aerations being dissipated and disappearing in the flow. But right now in Notice, what I have noticed is that this problem seems to have been fixed. So so I think this is just a problem of TIDIS at the time. Okay, so moving to the 3D simulations, as we can see during the generation process, it's very similar to the 2D. It's just extended to a third dimension, but it's pretty similar to the 2D. You have the rise of the flow, and then you have overshoot, basically a small overshoot, and then became aerated. And during the propagation process, you have a braking roller, you have a turbulent braking roller, and you have a lot of air pockets, staying in the flow, like during the 2D. Again, that was the problem of the model. But if you're looking at the 3D simulation for the roller, it seems, again, less aerated than what you can see in the experiments. And also you see this very big slope of water going up to the roller, where you don't really see that as obvious in the experiments. So there's a difference between the two. Bear in mind that these two, so the numerical model and the experiments, are conducted at the exact same boundary and initial flow conditions. So they were basically exactly the same type of flow. So looking into aeration, which is always a challenge in numerical modeling and in experiments, and the validation is very complicated in this area. So experimentally, if you were to study the aeration or the void or liquid fraction in the flow, you could deploy an array of conductivity probes. So we use dual tip phase detection probes, and we use 3 of them because of the nature of the flow that is very rapidly varying. And since we don't really have a trolley that moves exactly at the speed of the wave, we had to put the probes at rest in a single location and then just wait for the wave to pass. And that is a very quick. That is a very quick process. Takes less than a second. So that's all of the data that we can handle. But again, with the numerical modeling, we have the whole process of the propagation. So here at the front, you can see this is the experimental data, and at the back, this is the numerical data. And we were able to average over 10 time increments. So we get this results over 10 time increments. So this is actually averaged, but the experimental data were instantaneous. And the void fraction is defined as the concentration of air in a particular location within the water flow. And liquid fraction, on the other hand, is the opposite, which can be calculated by 1 minus the void fraction, and it represents the amount of water in the water. So experimentally, we measure it using the conductivity probes, but numerically, we can use the color function to represent the amount of water within the flow. So when it's 1, it's completely 100% water, and when it's 0, it's 100% air, and when it's in between, we can approximate it as 30% of air. As you can see in this comparison, the experimental data actually shows much less aeration compared to the numerical data, and they're on the same scale. So they're on the same scale, which is opposed to what we just saw in the experiment, what we just saw in the videos. And that is, again, a very interesting finding, and that is the challenge of validation. Sometimes you just see inconsistencies. When we study turbulent flow, another interesting point to look at is the vorticity and the turbulent structures. With numerical models, it's relatively easy and now commonly applied to use vector fields to calculate vorticity. It's relatively easy to calculate vorticity, and then if you want to visualize the turbulent structures, you can use the lambda function to visualize the turbulent structures. So here on the left-hand side is the numerical results. The color of the slices, they are actually the vorticities, and as you can see, they're pretty consistent colors. So throughout the numerical domain, you get vorticity that is less than 100 or minus 100. So the magnitude of vorticity around the main flow direction is actually within plus or minus 100. And the black arrows are actually the velocity fields. So as you can see before, the passage of the wave, they are very regular. They're basically all going in the main flow directions. And shortly after the passage of the wave, you see a lot of circulations, a lot of lateral structures happening within the flow and also in the air. And most of them, you find it either near the corners or at the bottom of the flow. And then about 2 meters downstream of the breaking wave, you still have a bit of structures. You see these bubbles that's there, whether it's realistic. It's not sure if it's realistic, but you can see that the air is still very turbulent. And if you look at the structures here, they are both numerical results as well. So if you look at the structures before the passage of the surge, there are a lot of structures in the flow, but they're mostly of the same size, and they're pretty regularly distributed. So they are pretty randomly distributed. But shortly after the passage of the breaking surge, you can see that there are some large structures formed in the flow, and they're mostly in the lower part of the flow. So how do we study this experimentally? Well, because we don't have a PIV, and even if we do, PIV is not really functioning very well in a highly aerated flow, and especially in the roller region. So in my study, I used an ADV profiler. So we were able to measure the velocity not at a point, but at 35 points at the same time. And we were able to profile the velocity in a 35 millimeter by 35 millimeter frame of window. So there, we can then conduct cross-correlation analysis within that window to determine the turbulent scale of those structures. Of course, the level of resolution there would be within a 35 times 35 window. So that's what we get. So this is the experimental data. That's what we get experimentally. So before the surge, we have what seems to be two pockets.
Sophia, can I just interrupt you for a second? Sorry.
Yeah.
We might be having a problem seeing your slides. So you've moved on from the validation, vorticity, and turbulent structures slide, haven't you?
No, I'm still there.
Oh, I'm sorry. Okay, great. Awesome.
Sorry. Is that possible if I ask? So can you see my the arrow moving? Like, can you see that? Because I try to highlight.
There it is. Back again now.
They're back again.
Yeah.
So you can see the arrows.
Yes.
Okay. Cool.
Yeah. Sorry for the interruption.
That's all right. So can I move on?
Yeah, please.
Okay, so sorry, I still need a bit of time to explain this slide. There's a lot of information here. So
no problem.
As you can see here, before the passage of the wave, you see two pockets of seemingly horseshoe structure. That's just a hypothesis. I'm not really sure what sort of structure that is appearing here, but we seem to find experimentally that there are two pockets of structures here within the flow before the passage of the wave, and then shortly after the passage of the wave, we see them breaking up into or merging into a much bigger structure. And that seems to be confirmed by the numerical study. Now, I also want to highlight that because experimentally this is within a 35 by 35 millimeter window, and in the numerical model, the finest mesh was 50 millimeter by 50 millimeter. Because of the time constraint, I wasn't able to refine the mesh further. So that is why even the smallest structure found numerically was actually bigger than the whole window of the experimental study. So it is not possible for me to compare quantitatively the size of the structure that we found experimentally and numerically, but qualitatively, it seems to both models seem to suggest that there were small turbulent structures and regular structures before the arrival of the wave, and after that, they would merge and became larger structures. So now we're moving on to field measurements. I won't be talking too much into the field measurements because validation nowadays usually are limited to validating your numerical model against experimental data. But again, field measurements seems to be more realistic and than the experimental data. So even if you were doing experiments, it needs to be validated against field data as well. And that is something that a lot of experimentalists cannot do or doesn't really have the ability to do. So the one problem with experiments is that it has scale effects. Namely, that means that if you were, say, doing experiments in a 1 to 10 model, for example, you are inherently having a scale effects. That means your model is much smaller than the actual prototype. There are certain characteristics that just doesn't scale down like 1 to 10 in your model. So for example, if you were studying a free surface flow, usually we would use a float similitude. That is, we would ensure that the float number in the experiments are the same as it is in the prototype, but your Reynolds number is most certainly going to be different. So if this problem concerns the viscous scales or like the viscous structures, and your Reynolds number is drastically different, then your model is probably not reliable. Your experiments are probably not that reliable. On the other hand, if you were focusing on the Reynolds similitude, that is, you try to make sure that your Reynolds number is the same model and prototype, then your float number is going to be different. And if the gravitational force is playing a big part in your flow, then your experiments are probably not accurate. And how can you ensure that the Reynolds number and float number and all the other dimensionless numbers are all the same between your experiments and prototype? Well, it's just not possible. So either you're doing measurement directly in the real flow, a river, an ocean, for example, or you're always going to have scale effects. So why don't people just go into the sea and do measurements? Well, it's going to be really hard, and it needs a lot of people, and sometimes it's very risky. Most of the time it's very risky, and sometimes it's just inaccessible. So that is the challenge with field measurements, and it's even harder than doing experiments. So I will leave it at that. Okay, so the second case study is a fish-friendly culvert design. So this case is very interesting because I was, even though I was the last person to work on the project, I was able to basically see through the whole process. And because I was able to see through the whole process, I can basically generalize the challenges or the pain of the project from the start to finish. So the project is to design a culvert that is friendly for fish, basically. And the reason why initially our culvert in Australia is not very fish friendly is because with the current design standard for engineers in Australia to construct a culvert, the primary focus here is to do it as cheap as possible. So you want to have the smallest size of the culvert to pass the largest size of flood. And that means that you would have a very narrow throat, and the water going through that throat is going to be very fast. And that fast flow is particularly harmful for local fish, especially the baby fish, the juvenile fish, because their swimming ability is very limited. So their swimming ability is sometimes less than 0.5 meters per second, and the flow through a culvert during the design flood is easily several meters per second. So when that happens, it is pretty much impossible for the fish to swim against the flow and go upstream to basically build a habitat and having babies. So the goal in this project is to develop some sort of a guideline as to how to construct a culvert that would allow flow to slow down like a lot during not exactly a design flood, but during most of the time in the year. So current practices for retrofitting the culvert, but when we were doing the project at the time, the current design guideline that offered by the biologist and the fishery regulation authorities is that you need to make sure that the culvert, the flow within the culvert is less than 0.5 meters, 0.3 meters per second, even or less, and that is just not possible to implement. Or they would advise you to use baffles or ribs that would slow down the flow on the side, but first it would also slow down the efficiency of the culvert as well. So it would make, so initially the culvert might be able to pass 100% of the design flow. After the implementation of those baffles, it could easily just pass 70% of that. And also it can be dangerous for people as well. So if you were somehow swept by the flood and ended up trapped in the culvert, and you could hurt yourself when you hit the baffles or the ribs. So there were safety issues as well, and you could have debris trapped in those places. So there are also sort of problems. That's why engineers were very hesitant when it comes to putting in large-scale structures in the culverts. So we were trying to find a way around both problems, and that's the idea that we came up with, is that instead of slowing down the bulk velocity, that is the average velocity within the culvert, we try to focus on the local velocity, because fish like to swim near the corner and the sidewalls because the flow were just slower there. And instead of passing the fish at design flow, which doesn't really happen in Australia that much, because Australia is overall a pretty dry country, and in most of the states you would have a flood only at certain period of a year, and for most time of the year the flow is pretty low during in the creeks anyway. So we were not going to focus on passing the fish during design flow. We were going to focus on passing the fish at some point less than the design flow, so maybe 10%, 20% of the design flow. But then even after establishing those ideas, we still need to know the whole picture of the flow within the culvert. So we need to know the velocity field everywhere in the culvert. That's why CFD modeling has come in. So the experiments, we did some experiments within the facility that we could have in the University of Queensland, and we had a long channel that can be used to model a rectangular culvert, and then we had this box culvert model. I think it's 1 to 10 box culvert model here, and we were able to use this to have a good idea of what the flow would behave around the culvert. So this is not really used extensively in the experiments. They were just used to get a reference of the flow behavior around the culvert, because sometimes you could have a hydraulic jump forming downstream of the culvert, and the forming of the hydraulic jump sometimes can be pretty hard to predict. So that's why we use this just to see what is going to happen downstream of the culvert. And the tool that we use most of the time during the developing of these design guidelines is CFD modeling. So it seems to be a very easy model to build. You just have a rectangular prismatic domain with, you know, inlet on the one side, outlet on the other side. You have walls on all of the other boundaries, and you impose basically an inlet velocity and an outlet pressure. So you could have the depth within the domain that you want. And of course, the outlet depth were calculated using some analytical solutions, or use the experiments that you measured to just have a realistic outlet depth. And then we can get basically the flow field throughout the whole channel. The model that we used were standard key epsilon, obviously due to the fact that it is a very quick model. We don't need to run a DNS that takes a whole year. So we used the standard key epsilon, and we used VOF because still we have two phase of the flow. And then all the models were done on a staggered grids that are gradually refining near the corners. So we want to have better results near the corners and near the walls. So, okay, we're doing numerical modeling, so we need to validate the model. The way that we did the validation was that we had experimental data for two certain flow rates. So we had a flow rate of 56 liters per second, another one with 26 liters per second. And we were able to validate the numerical model against the experimental data. As you can see, with the larger discharge, we have a pretty good approximation near the wall, that is 8 centimeters from the side wall. And then we have a not so good match in the center of the channel. So this is the channel center. In the center of the channel, we're not having a very good match. But then within the wall area, we still have a pretty good match. Here with the smaller discharge, the match was better. So whether it's near the wall, that is also 8 centimeters from the wall, and that is in the middle of the channel, they're matching pretty well. They're matching, both are matching pretty well. But the problem is we only had that 2 sets for validation. And to develop the guideline, we have to run numerical model for a lot of flow conditions, at least like 10 or even more. So there is a table of all the flow conditions that we run, and only the purple highlighted ones had experimental data to validate against. So that's one challenge that comes with validation, is that your numerical model is very flexible. You can basically change a number and then the model is fit for another set of flow, but you cannot do that in the lab. You have a certain size equipment and you have to stick with it. So we only had 3 data sets to exactly validate the numerical model, and then the rest of them were basically model only. So at the end, what we try to achieve is we try to have a design chart like this. So we have a dimensionless design chart that would plot the percentage of the flow area against the percentage of the bulk velocity. So by doing that, you know, in the field, they could very easily, as long as they come up with a set of flow, inflow velocity, culvert dimensions, they were able to calculate the bulk velocity pretty easily. And then they were able to compare it and see, you know, how much percentage of the flow area is less than that velocity. So see if they have a target fish speed that they want, and they were able to, they can easily find the percentage of the area within the flow that is less than that swimming speed of that fish. And if it doesn't satisfy, what they want for the fish, then they can increase the size of the culvert and then do the reference again. And we fitted a basically empirical equation within the data that we have, and that is the equation. So instead of using the chart, they can also use the equation to get the area that they want and see if it satisfies their guidelines or their target. So as you can see in this chart, the blue symbols are experiment, and it's not just experiment that we did here in UQ. They also included a lot of experimental data previously done in rectangular channels as well. And the black symbols were CFD that were done prior to our studies, and you can see it's not that much. And the red symbols were what we've done. So all of these red symbols, only some of them had validation. So even though they look like that they really lie within a small margin of scatter, however, we can only confidently say that we validated some of them, not all of them. Okay, I need to wrap up quicker. So a bit of honorable mention of other studies that was done within the same project, but deal with different problems. So at a point in the project, we proposed some small corner buffers that can provide shelter for the fish. And we did experiments here and numerical modeling here. And you can see the results are not very similar. So with the experiment, basically all the flow were mostly less than 0.6 meters per second, but then in the CFD, most of them were higher than 0.7 meters per second in velocity. Again, another type of structures that we try to test is a longitudinal side beam, because it was suggested to be effective for fish. So we tested it here experimentally in UQ, and then we did some numerical modeling of the same flow as well. And then as you can see, it's not that similar. It's got similarities there, but it's not that close. So to sum up, why is validation important? Well, it's pretty easy to see the importance of the validation being that you have to make sure that your CFD is generating realistic flows. However, there are a lot of issues and a lot of challenges within the process of validation. So the first one being you have to compare apple with apple. So if you were trying to validate a turbulent flow against a turbulent flow, you have to validate the exact same characteristics against each other, and you have to have the exact same flow conditions. So you cannot compare a very slow flow with a very fast flow, for example, and you cannot compare a propagating wave with, say, a standing wave or a stationary wave. So sometimes you just don't have the right apple there. Another thing is your numerical model are flexible. You can change the number and it's a different flow, but experimental facilities are fixed there. Your numerical models are non-intrusive. You don't have to put a probe into your numerical model to measure things, but experimental ones, sometimes, most of the time, they are intrusive. Numerical models, they're run by computers, so you can run, under ideal condition, you can run the models day and night, 24 hours a day for 10 years, but experiments, obviously, they are run by human beings, and it is not possible sometimes to do the measurement at every single point of the flow. So what if you don't get a match in the validation? Does that mean that your numerical model is wrong? It's not necessary. Sometimes the first thing that people think is to refine the mesh and try again, but a lot of times it's not something to do with your mesh. It sometimes is the problem with your model. So if you're using K epsilon, you get a certain result. You were using LES, you get another. And also the method that you use for discretization, the algorithm that you use for advection equations, convection equations, that all comes into play, and you don't really know which is the problem until you try the right one. And sometimes it's just the experimental data is not accurate. As you can see, a lot of instruments, they are intrusive, and a lot of instruments, they're pretty basic, like the pitot tubes, they're very, very basic. And even though they're pretty reliable in simple streamwise flows, they could be not that reliable when turbulence is very intense in that area. And what if you have a match in the validation? You know, how good is it good? 10%, 20%, 1%, you know, with the culvert study that we had, the biggest, I think the biggest difference between experiments and numerical results were about 10%. And when we were trying to get the result published in the journal, one reviewer did say that it's 10% good enough. And we try to justify that within the field of engineering, 10% is pretty good. But, you know, sometimes you just want that result to be accurate down to 1%. And, you know, how good is good enough? So, and those are all that I want to talk about. Thank you very much for your attention. Here are some references, and we still have some time for questions, hopefully.
Yep, great. Thank you very much, Sophia. Was that a real fish in your experimental setup a few slides back?
Well, yes, there were at a point real fish, yes.
Yep. Do we have any questions for Sophia? While people are kind of, you know, reflecting on your talk and thinking about questions, I just had a question. So in where you have that aeration bias in the tidal bore simulations, is that a result of the non-monotonicity of mass fluxes at the free surface in that model?
Sorry, can you maybe go down to the slide numbers?
Yeah, it was an earlier, yeah, before these, the 2D ones probably show up more clearly, where you had that aeration bias and you had all that. Yeah. Is that a result of like a non-monotone flux scheme at the free surface?
To be honest, I don't really know. At the time, like I said, at the time they were using a code called Titis, and now they're developing a new code from scratch called Notice. So I was able to check Notice if they have the problem that you have, but I couldn't say about Titis because I don't really have, I can't go into that code anymore.
Yeah, sure. Okay. Be interesting to know if they are using a monotone scheme at the free surface in the new code, and if so, if you're getting the nice, you know, sort of turbulent nonlinear bore structure still in that new code.
Okay. Yeah, I might be able to ask. I'm working with the people right now, so I might be able to ask them this question.
Yeah.
And I'll give you the answer maybe afterwards.
Yeah, no, I'd be curious to know. Do we have any other questions for Sophia? If you do, you can either unmute your microphone or alternatively drop them into the chat window below. Just another question as well on the tidal bore simulations. Did you do sort of like a sensitivity study of the different parameterizations? Like, did you sort of sweep through like a finite number of you know, LES coefficients and things like that and look for sensitivities in those parameterizations?
Yeah, right. So with the 2D simulation, so there were no strict sensitivity analysis done for that because first because I was doing it during my PhD and I had obviously a finite time frame for that. Yep. So I had a 3-year time frame basically, and I only did numerical simulation for half a year. Most of them were experiments. Mm-hmm. So within that, for the 2D model, I think I did maybe 3 steps of refining, and that would be it. And at the time, I wasn't really following a guideline of because there wasn't really a guideline to follow at the time. Not much study were done before me on this specific phenomena. So I did a 3 steps refining of the mesh for the 2D. And once I got that, I tried to move it to the 3D, but then the 3D were moving slower than I thought. So I wasn't able to use the finest mesh going into the 2D, and I had to sort of coarsen up the mesh a little bit for the 3D. So
Was
really,
the 3D, was the 3Ds in parallel?
No, so I did 2D first and then 3D next.
Oh yeah, but that, sorry, they were serial simulations, were they? They were all done on one processor, the 3D ones.
Oh no, it was, yeah, it was parallel processing.
Oh, okay, cool. Do we have any other questions for Sophia? I can't see any in the window there. So it's 5 o'clock, so I should probably wrap up now. So thank you once again, Sophia, for a great talk. That was really enjoyable. And yeah, thank you very much.
All right, so see you.
Yep, see you. Thank you, everybody. Hope to see you next week.
Yeah, thanks. Bye-bye.
All right, goodbye.
Thank you, Sophia.